Welcome to the video. My name is Ryan Quillette, and today we're going to go over sine data reduction. We're going to cover why sine data reduction is unique. We're going to do a step-by-step guide to analyzing sine data, and we're going to use the example project included in the software to save some time, and I'm going to show you some key takeaways and some tips and tricks for handling trickier data sets. So why do sine data reduction? AlgebView helps simplify sine sweep tests by breaking down frequency and amplitude from time domain signals. This method gives clear insights compared to traditional traces like, say, FFTs or transmissibility. The big benefit here is we can better understand how the system reacts and identify resonances at different frequencies. So here is a sine sweep, and we can zoom in and take a look at it, and sure enough, there's our sine tones. But how do we analyze this data? Well, one way we could do that is with an FFT. But if you look at FFT, of course, it's just going to look at one point in time, right? So if I kind of pan this through, you can see the peak of the sine tone changes. So that's not going to work. One thing that we could do is we could do a peak hold FFT. So let's add some peak holds in. And that's going to give us closer to what we're looking for, where we're looking at the peak values over frequency. But that's still not exactly what we need because this also includes some out-of-band information, and it suffers from some issues with the tones being able to sweep too fast for us to be able to track perfectly with an FFT. Another way I see people try to analyze this data is they'll add a power spectral density graph. And that has a lot of problems because it averages out information, and you can actually see the amplitude drop with frequency. Or I'll see someone try to analyze it with a transmissibility graph if they're trying to get a ratio. And then that's going to have the same issues as the PSD, where we're doing averaging basically over time. And it's not going to give you the information that you're actually looking for. So that's the problem, and what do we do about it? So here's the sine data reduction example project that's included with AlgebView. You can find it in the link displayed on the screen. And this is going to give us a really good idea of what sine data reduction is and what it can do for us. So we've got some lines kind of tracking the peaks of these sine tones. Here I can zoom in, you can see this green line is now tracking the peak of this purple. And below that, we have the frequency, which is another generated trace. So here's our frequency. So this is 140 hertz, and up here, this would be 174 hertz. Pretty neat, okay? So that's on the time domain side of things. What we can also do from there is put that into a scatter plot versus the frequency. So we take this green trace here, and we take this purple trace here, and we put them together. So that is what we see here. So this is channel 3, and what we're looking at here is channel 3 amplitude versus frequency. And this is the type of trace that you're used to seeing on a typical vibration test report for sine data. Additionally, we have things like velocity and displacement shown, and then transmissibility and phase, and even a more interesting one, which is transmissibility versus phase, which can tell us the peak transmissibility phase angle. Great, so you want to do this for your own data set. Let's first start by saving some time by reusing the sine data reduction example project as a template for your new recordings. We're actually going to take this project and say, open it with my own recording. That'll save a ton of time. One thing you have to make sure is that your recording has some kind of a frequency reference, like a cola or an output that we can track to figure out what the frequency is. If you don't have that, I will show something at the end of the video to show you how you can manually reconstruct that frequency versus time channel. So to reuse the sine data reduction example project as a template, first open it once, so it's at the top of the list. Then right-click on that item, and then say Open Project with Other Recordings. From here, we can pick our next project to open, our next recording to open. And this doesn't have to be a VFW file. It can be any type of recording file ObserView supports. But this is going to be my next one to analyze. So let's open that up. That's going to create a new window of ObserView and then load in and apply the sine data reduction math equations to the new data set. Okay, it's finished loading in. And now we can take a look at how this looks. So the length of the recording is slightly different, so I need to grow the range I'm looking at. But it has mapped a lot of things correctly. So what we want to do now is start correcting our math equations to match the new recording that we're looking at. Click on the math button here. And the first thing I want to adjust is the demand. So in this case, I have a constant acceleration of 0.5 g. That was my demand line. And now I need to go to demand. And I actually have this set up to do a combination of a constant displacement and constant acceleration. But we need to simplify that down to just the constant accel case. So let's remove most of this equation. This should actually be G. And now let's take a look at the result. So we have a demand line at half a G going through, and then we have our abort lines, and you can adjust the aborts and tolerances also, looking at the math. And we can see that it has mapped onto this quite nicely. And I didn't have to do very much work. So that's exactly what we want to see. One thing you'll need to do is adjust the start and end. And if you have a sweep up and a sweep down, you'll want to keep that in mind, because what this will do is it's going to show all the sweeps ups and sweeps down on top of each other. So what you might need to do is shift the time window left and right in order to analyze the section that you want to analyze. So we covered how to do this the easy way, just reusing an example project and applying it to a new recording. Now I'm going to show you how to do this step by step manually. First, we need to create a frequency trace versus time, and we do that by using the freq command followed by the channel that we want to track for frequency versus time. I'm using output here, and cola would be another really good option. After you have the frequency defined, we want to define a track sign, which is going to be track sign of something like channel 1 or channel 2. And then the second argument is the reference. So we're going to use the same reference channel that we used for frequency, which is output. You could also use cola here. And then that will output a peak G versus time trace. You can also have that project into a peak phase versus time trace. Next, let's look at phase relationships versus time. So to get phase, we can do phase of the track sign, and then that will output a phase versus time. Velocity and displacement, we can calculate by doing something like channel 1 sine, which is our track sign of channel 1, and then dividing by 2 times pi times frequency. To calculate displacement, we're going to do 2 times channel 1 sine divided by 2 times pi times frequency squared. Lastly, transmissibility is going to be a track sign of channel 3 over output divided by a track sign of channel 1 over output. To analyze this in the frequency domain, what we want to do is create a new scatter plot where we take the track sign versus the frequency trace. Combining these two, we'll be able to plot acceleration, velocity, and displacement traces versus frequency. So for example, we could take channel 1 sine as the y and plot that against frequency as the x. We can also look at signal-to-signal transmissibility by using the transmissibility trace that we created earlier. The reason we want to use transmissibility is to look at how signals interact with one another versus frequency. When looking at phase versus frequency, we want to look for resonances by looking at the phase and seeing if there's a rapid change in phase, particularly if it goes positive 90 or negative 90. This indicates a resonance. Transmissibility versus phase is an interesting thing to look at also. What this is going to do is give you an arc, and the peak of the arc is going to identify what phase value results in the highest transmissibility for that resonance. Here's some tips for some trickier data sets. So track sine, we can specify some initial parameters. One of them would be the fractional bandwidth, and the next one is the fixed bandwidth. By default, we're going to have this be relatively wide, but you might want to narrow it. So let's set it to 0.05, for instance, and also make the fixed bandwidth tighter, say maybe 5 Hertz. This is going to create a narrower tracking filter that's going to remove frequencies even more than before, but the downside is going to be that it won't be able to track as quickly. You can also do the opposite of this and increase the bandwidth. Another thing I'd like to show is cases where you have average control or max control for sine. So first I'm going to take channel 1 and say channel 1 and channel 2 are part of a max control. So this is going to be channel 1 dash sine, and then I'm going to duplicate this, and I'm going to change this for channel 2 and call this channel 2 sine. And now when I want to combine the two into one, I'll just do the max of channel 1 and channel 2. So that gives me a max there. And let's say I want to do average control. Just duplicate this again and change this to mean. And now we have a mean control trace. If a project lacks the necessary frequency reference channel, like a cola or an output, we can still track this data, but we have to manually create a trace to do that. There is a way to do this in the software, but we have to enable a feature that's in Technology Preview. So go to Settings and then Technology Previews, and then we want to scroll down until we find the option Create Math Channels by drawing points on time spectrogram graphs. From there, we're now going to create a time spectrogram graph. Go down to time spectrogram and pick something like channel 1 to track. Here we can see a very clean line, and this is what we're going to use to track our frequency versus time. Convert the frequency here to logarithmic because this was a logarithmic sweep rate. That's going to create a straight line for us. We also need to adjust the maximum frequency of this so that we can get the whole sweep. I know that we swept up to 1,000 Hertz in this test, so I'm going to put this maximum to 1,500. So now I can see the beginning of the test and then all the way up to the end. Next, we need to go to Properties, and then there's a new option, Frequency Reference Builder, and we can do Start Edit. So I'm going to click here, and then I'm going to click here, and then I'm going to scroll up to here and zoom in and get my endpoint here. Once we've done that, click on Generate, and then that will create a new math function that represents this line versus time. So I'll scroll down to the bottom of the list here, and here it is, generated TAC. I'm going to rename this to Freq 3, because I already have a couple other frequencies defined. And then the output unit's going to be Hertz. From here, I'm now going to create a new way to track channel 1. That's going to be using the tracking filter function, which is a little bit different than track sine, because what we're going to do is give it an actual frequency versus time data set. So the input will be channel 1, and then our frequency reference is going to be Freq 3. And there we go. We've now created a tracking filter for channel 1 following our custom frequency 3 math trace. Here's some tips. Focus on relevant time segments for more accurate data. And what I mean by that is trim the data set so that we're looking at the start of a sweep up to the end of a sweep and not extra information like the ramp up and the ramp down. Ensure that the input and output units match to avoid errors, of course, and use the example project to set up things quickly for similar looking tests. You can also create your own template projects and reuse those on further analysis projects. So what are our key takeaways here? ObserView helps simplify and enhance sine sweep analysis. We can follow the step-by-step guide here for getting consistent results. And if you start with the example project, that'll help save you a lot of time in your analysis. I hope you enjoyed what I've shown you here today. If you have any questions, please leave comments below or feel free to reach out to support. Thank you.